Hopefully that worked. Did people get the notification that it's recording? Cool, awesome. Okay, so before we get started, since I know people did have the chance to look at the PowerPoint, there were 3 questions at the end. If anybody wants to respond to any of those, and I'll pull them up too. I'd love to get started just by people either putting in the chat or just unmuting and saying like any thoughts they had about the videos, or about the questions that were in these questions that were at the end. Does anybody have thoughts? It's also totally fine if you don't. These are definitely like very questions that I think about a lot, that are definitely hard things to think about if you just seen these data for the first time. Videos. All right, well, I'll start off. I can just kind of go through where, so we got one benefit of analyzing videos is that you get to see the path of the particles, which shows the structure they're in. The photos might only show single points where there's space for the particle to exist, but not the entire space. Yeah, that's an absolutely great point, Laura. And I think that's really like one of the primary benefits of this work, of using this this technique to capture these videos, and then get the trajectories, is we really are interested in how they're exploring the space and how their motion tells us about the surrounding space. And so just a picture of it doesn't really tell us anything about its longer term motion. So yeah, that's spot on. Cool. One potential drawback that I often think about, for this question too, is just it's a huge amount of data. Instead of it being one image, it's literally 651 images stacked on top of each other. And so just computationally it's super expensive. And so that's just always kind of a struggle to deal with on the technical end, is how to manage all of that data. Yeah, and I think we kind of hit on point. Laura kind of hit on point 3. So, all right, we're gonna, if anybody has thoughts about these afterward or during, feel free to put them in chat or anything. But yeah, let's go ahead and get started. So as I'm going through this today, we're basically just gonna be going through a notebook, exploring some of the MPT data for the first time, thinking about some visualization tools and statistical tools we can use to get a sense of our data before we jump into machine learning on Monday. So any point this something's confusing, I'm going too fast, too slow, you want clarification, you just want to know more, feel free to unmute and ask, raise your hand, put it in chat. This is designed to be really as interactive as possible. We'll have some points where we get to blocks of code that I'm going to want you to spend some time playing around with, changing some stuff up. So yeah, let's get started. So the first thing that we're going to need to do is actually import all of our packages. We're going to import, pandas as PD. Going to import NumPy as NP. Going to import matplotlib dot pyplot as PLT. From from OS, we're going to import list dir get CWD chdir. Actually, one thing we're gonna need to do first, I'm just gonna put this in the cell. We're gonna use a new package today. I don't think anybody's used before, but it's a package we developed in the Nance lab called diff predictor. And if you put this little exclamation mark, and then run diff predictor, then pip, that's what I missed. Pip install diff predictor. Then should download it for you. If anybody has trouble with this, let me know. Oh, apparently I have trouble with this. Already satisfied. Oof, that's annoying. This worked yesterday. Are other people having this issue as well? Double check, import data. Access. Okay, same issue. Might as well just double run it. Looks like I don't know why. I guess I just ran it again and it worked. To be honest, I have no clue why that actually worked. But let me know if running it the second or third time did not work for you. Yeah, I still don't know why it worked for me. Cool. Okay. So now we're gonna get access to the data. So we're gonna say work book dir. So this is our working directory, equals get CWD. This is gonna get our current working directory. I like to just always double check to make sure I'm in the working directory I think I'm in. So we can do print current notebook dir. And we're gonna plus our work book dir. Okay, we can run that. Okay, cool. We're in content, which is right where I want to be since this is our content. Next, I am going to do chr. So this is changing directory. Actually, wait, in this case, I don't actually think I need to do this. Don't do that. Instead, what we're gonna do is set our data path. So I have my data path as, so I'm in content. I have content going to drive, going to my drive, going to Nance lab, going to textile, going to MPT data. So if you open your like file navigator thing here, what I like to do is just copy the path, and then we can say our data path equals that. Then make sure to add like a little forward slash at the end. If anyone has issues figuring out their proper data path based on where they store their data, let me know. That should just run, yeah. And then what we're gonna do is we're going to just make a list of our files, just to make sure when we go through that folder, the only thing we are actually downloading is our data. So we're going to say file list equals F for F in list directory, lister, data, path. If is file, so this is just checking if it's a file, or join is file, join data, path, F. We'll say and feet. Oops, yep, feet. So we're just doing that because all the files start with features in F. It's not defined. Oh, did I forget to? All right. I totally forgot to have you download or load in one more. Okay, so go back up to where you are importing your packages, and we'll do from os.path import is file and join. We'll also do import, oops, new line, import Seaborn as SNS. So that's, I think people probably used Seaborn before, perhaps earlier, but it's just a really nice visualization package. Okay. So now we can make our file list. And then I just like to double check usually that my file list is actually what I think it is. And so mine should be 70, everybody should be 75 files. Cool. Does anybody have issues with getting access to getting the data uploaded here? For now, I'm going to take that as a no, but if that's not true, just let me know. So now we have 75 CSV files with data. And it's just really kind of not fun to work with 75 files at once. So the best way that I figured out to do this is basically to figure out how to combine them all into one big pandas data frame instead of a bunch of individual pandas data frames or a bunch of CSVs we have to read in every time. So we're going to call this fstats tote. So this is just saying feature statistics essentially. That's just going to be our variable name. You can name that whatever you want, but that's just what I commonly call it. And then this is where we're going to use this data process function. So this is a function I wrote to basically combine all of the CSVs I work with into one data frame so that it was just easier to work with. So let's say data process, and then we're going to call the generate full stats method. And we're going to pass it the data path. Oops, data underscore path. We are going to pass it the file list we made. And then we're going to tell it in a list. So in these square brackets, we're going to tell it the different ages we want from the data set. So the data set has 3 different ages, and we want to specify that we only want files that are from those 3 ages, not anything else. So in here, we can put P14, so that's our rodents that were aged 14 days, that were at age 14 days. Do P35, and we'll do P70. Oops, P70 as a string. And then we're just going to tell this function what we want to. We're going to basically add a new column in the data frame that tells us for each trajectory in the data set what age class is it from. So basically now we're going to have like a really long data set that has an individual trajectory as each row, and it has a bunch of statistical features about it that we're going to try to analyze, but we want to know like which age they're from. So we can just call this age, at least I usually call it just age. And then it should run. It's going to tell us all the files. There should be a future. I'm assuming you all will get a future warning. Basically, I need to go back and change my method to use a different something besides append, but it still works. It will just be at some point in the next year or so, I'll have to change that. So it's gonna take a little bit just because we're gonna have to combine 75 files together. Shouldn't take too long though. And we can just get ahead of it by starting to write out some code that we'll need when it finishes. So first thing we can do is call this fstats_tote.head function. So this is going to basically let us look at the first 5 rows of the data set and some of the columns and just be able to see what's in there. So we have track ID. So this is basically the numbered particle. So for each video, there's X number of particles. It varies. And this is just a unique identifier. Then we have all of our statistics. We won't go too much into what each statistics is today, what each specific statistical measure is today. But basically, it's looking at the shape of the trajectory and calculating different things about it. So elongation is if it's like really long or really condensed. Dfit is like the diffusion coefficient, so how fast it was moving. And we calculate mean and standard deviation of all of them as well. And so we can also like print out what all of them are. So you can say fstats_tote dot columns. And so we actually have a lot. I believe there's like 93. We won't use all of these. We'll focus on a very specific subset today. This is just a nice way to look at all of the things, all of the potential columns we could look at. And we're only going to focus on a few, a small subset. I'm hoping this will work. I'm going to send this next block of code in the chat. Oh, can I not paste into there? Oh, no, oh, maybe I can. Okay, that's weird. I kind of thought I could paste. Well, all right, we're going to write it out. So this will be a little laborious, but we can just focus on a few. So we're going to say our feature list. So this is the list of statistical features we want to look at. So oops, not that. We have a bunch of them, but we're just going to focus on a small number. I'm just going to choose 5, not for any really particular reason, just because I don't want to have everybody have to type out a ton of them. I'm going to post this final notebook. I'll post it, and it will have all of the features available that all like named. So you're more than welcome to use that later, or you can use this fstats_tote.columns to pick and choose. I recommend using just anything with mean in it is usually pretty good. So yeah, we're going to start with do mean alpha. We'll do, let's see. Oops. Mean def1. Let's do mean boundedness. Mean boundedness. Mean asymmetry 1. So yeah, feel free to copy the ones I'm doing or do 5 or more of your own. I'm totally up to you. Oops. And mean, we'll do dfit. Okay. So now we have, feature list is not defined. Forgot. Feature list equals, cool. Then we have, that's our list. So now we're going to do a little bit of filtering of the data just to make sure we don't have a lot of NaN values, so not a number of values, any like weird infinity or negative infinite values, anything that's would be really hard to actually analyze, and it's just the result of some issue going on with data processing that we don't want to analyze. So we're gonna make a new data frame. So I'm gonna call it ECM for extracellular matrix, since that's where these videos are taken. So we'll say ECM equals fstats tote, and then we're going to filter it by putting in the feature list, and we're also going to add on age. So this is again our class variable that will tell us for each trajectory which age group it came from. Then we are going to remove any values that are, like I said, weird, like NaN, infinity. So let's say ECM equals ECM, and then we're put some square brackets. Within the square brackets, we're going to do a little squiggly, and so this means not in instead of in. So ECM, we'll put that again in, and then do another square bracket. List set feature list. So this is kind of making a set of taking these here, and we're going to use that as a way to compare. Basically, we're using this to check, and we're going to remove two specific. Actually, in this case, we don't need to remove that. I'll do it. So if you end up including the mean diffusion coefficient 2, so mean def 2 or just def 2, we have to add this little set this little notation in. So oops, def 2 and mean def 2, just because these are taken at a later time point compared to mean def 1, and a lot of times directories are so short they don't get to mean def 2, but we don't want that to be a reason they aren't included in the data, because we have other ways of removing those if they are not that time scale. So this is just to make sure that these aren't being filtered out, even if they don't have values in them, because that's okay for that specific variable. And then to get it so we don't have any weird values, we'll do isIn, and then we're going to pass it a list of anything we want to cut out. So we're going to say numpy.nan. We'll say negative numpy.inf. And we will say numpy.inf, just normal infinite. And then we'll call .any, and then 1 to get the proper axis. And then we hope, okay, looks like I added an extra bracket somewhere, which is not surprising. Okay, I think it is right there. Yes. Okay, so if you made the same typo as I did, okay, that's fine. That's just the same warning. There should only be square bracket, open, circle, circle, or not square bracket, parentheses, parentheses, square bracket. There's definitely some weird syntax going in here, so I'm just going to pause for a couple seconds to if people are running into issues there. If you got this line to run with no issues, can you give me a thumbs up? Are people having issues with it? And can I help with what are those issues if you're having any? I feel that. Cool. So yes, give me a thumbs up when you get it, but no rush. This is definitely like a annoying syntax line. Yeah, totally. Yeah, anytime if you miss something, I go on too fast, just feel free to put it in the chat and I'll go back. So this one's just fstats tote equals data process dot generate full stats. Then we're passing it the data path passing it the file list, a list of our ages, and then just what we want the age column to be called. Okay, now I think you can see both of them, hopefully. I realized I could do that. All right, people made some progress on that. No worries at all. If you haven't quite finished yet. I'm gonna give just a couple more, like 30 more seconds. Then I'll try to write. The next code will be pretty easy to write. So if you haven't quite finished, shouldn't take too long to catch up. And then we'll take a little pause there just for a couple minutes. And then I can help anybody sort out any syntax issues. Okay, so once we have that, what we're gonna do is just gonna do ECM equals ECM dot fill in A with 0. So this, I don't think this will be too important here, actually, just because I'm pretty sure that this is mainly for the diffusion coefficients that we theoretically didn't filter out on purpose. But it's good to check just if we do have any leftover NA values that are for specific things we want to keep in, to set them to 0 is pretty normal. And then I just like to check the shape to make sure that I didn't break everything. Cool. So that's what I expect. So we have this is all of our data points. So we have 38,000 trajectories across 3 classes that we're going to look at. And then we have 6 columns. So our 5 features plus our 1 age column. Finally, the other nice thing we can do, again, we can just do ECM.head. And yeah, just look at the data. You can also do, if you wanted, ECM.tail, and that sense, instead of looking at the top first 5 rows, it looks at the bottom 5 rows, which is always nice. So yeah, okay, I'm going to stop there just for a minute or so. So people, if anybody doesn't have the syntax yet, they can look at it. And then we'll dive on into some more statistical analysis. Okay. People give me a thumbs up if they're ready to move ahead to the next section. Awesome. Sweet. Okay. So one way I like to start getting an initial sense of my data is to just look at the, I don't know, like the distribution of the data within specific features. So we can do here is we can do ECM, and we're specifically going to look, at least I'm going to look at def1. Feel free to put any feature that you have in there, or yeah, anyone that you want. And then we can do this method called .describe that I like. And so then we kind of get a sense of the just some generic statistics about it. So what the mean value in this is, what the standard deviation is, what's the like the 25th percent variable, what the max is, which this is very high, and probably would end up cutting this out long term, but that's fine for now. But yeah, we can do this with any feature that we have. So we can do, let's do asymmetry. No way, I spelled that right. Yeah. Asymmetry 1. Cool. So then, we have much different. So the mean is 0.77. The max is 1. So as you can kind of like notice, there's different, the ranges are different here, which is generally fine, at least for visualization purposes. When we do more machine learning stuff, we kind of have to scale them, but we'll get to that into later when we actually need to do it. So then what we're going to do is so this is just looking at the statistics on the features from all of the classes combined. We also want to be able to look at what the statistics are like for specific subsets of the data and like the different age groups that we have. So we can do is we can make 3 smaller data frames for each of our ages. So we're going to make P14 data frame. It's going to be equal to ECM. Then we're going to filter it by the age column. And then we're going to say we only want ones where the age column is categorized as P14. And we can just repeat this for our other ones. P35 is ECM, age. And feel free to just copy paste these new lines and then change the numbers since they're going to be the same. So this one's P70 equal to ECM, age equals P70. I'm gonna make sure that says DF, otherwise I'll confuse myself. Okay, so then we can do kind of the same thing we did before, but we'll do it just on P14. So we'll do P14 DF. Again, I'll look at the mean diffusion coefficient. def1, I'll do .describe. Okay, we can see that the max is the same, so it looks like that's where that value came from. What else is there's only 6,000 trajectories in here versus 38,000, so that makes sense. Oh wait, never mind. That's let's put mean def1 back up here too. You don't need to do this. I'm just gonna compare it. So you can see first, so the mean of the entire data set's 8.44. The mean here is 23 just for the P14. So you can see that that's pretty different. All the other variables generally seem pretty different too. So that's a good indication that for this variable, at least, it's different between our different age classes, or at least P14 differs from the mean, or like the mean of all of the classes together. So that gives us some indication that there is that the data is not just uniform across all ages, that there are distinct differences for different ages. So yeah, we can also compare this to, let's see, let's do P70 DF. Look at mean def1 again. Mean def1. Oops. Yes, mean def1. .describe. So you can see the mean is way lower. So the mean is 3.5. Max is only 12. 75 percentile is 4 versus 29. Even the 25% here is 14 versus 2. Both of them have a pretty low, I guess, even lower minimum. It's really low. So you can see here that there are some pretty significant differences. But right now we're just kind of looking at numbers. I don't know. It's hard to understand it as well. Visual representations are way better. So one way we can do this is to use a histogram. So we're gonna use matplotlib for this. So we'll do just plt dot hist. So it's really easy to do histogram with just hist. We'll just look at the entire data set here. So we'll do ECM, mean, def1. Again, feel free to choose your own, whatever variable you would like there. We'll also, one option you can choose to switch up what it looks like is hist type, so just the type of histogram. We're going to use step filled at first, but I'm going to quickly just copy this. If you want to do different options, you can replace, oops, I went too far. We'll just move you up. So feel free to replace step filled with either bar stacked, step, or step filled, or try out multiple of them. The other thing we can control is a number of bins. So this is how the data gets bin together, how wide the groups are of data that's being clumped into one bar of the histogram. We're just going to set this to 200 for now. I think the higher you go, the longer it takes to make it, and the bigger that output is. But cool. So now we can have histograms. We can see that most of the data is really just within this range of below 20, probably even below 10. And again, we have the 152 value, which is kind of weird. So that's why it goes so far. This is one way to kind of get an initial sense of the data. Did anybody try any other types of the hist type or bins that you want to tell us what it looked like, or if you want me to try them? I'm happy to try different combinations. And try. I don't know if I've tried step before. Step. So in this case, instead of it being like filled, it just has this outline. That's kind of cool. What about just bar? What does that look like? Honestly, I guess it's a little different than step, but it honestly looks pretty similar. Okay. So again, we can also look at differences between classes, and this is a really nice thing I like to do because we could use that describe method to look at some general trends, but it's also nice to be able to look at different visualize the differences between classes. So you can do here is do plt.hist, and we're going to have one be our P14 DF, and I'm going to look at mean def1, but feel free to choose whichever one you want. Just make sure that when we put in this second one, make sure you put in the same variable name, or the same column name. So we're going to do, I'm going to do 70 df and also mean def1. Where does this go? Say bins equals 200. We're also going to say stacked equals true. So this is going to make it a little easier just to visualize it. And then we can also just give us our labels, or give it the labels for the data. So we can do label equals, one's going to be P14, and our other one will be P70. And this should run. Cool. And so we have, again, very different distributions between, oh, one thing I forgot, so that we know which one is which, is plt.legend. And then when it runs, we can see that the blue is P14, and the orange is P70. So there's just a much bigger spread of data for P14 than P70, whereas yeah, P70 is just all really, really low. We can also do is try adding all of them in, which I don't know if I've actually done this recently, so I'm not sure how messy it's going to get, but we're going to find out. P35 DF mean F1 F1 and then P35. Okay, so now we can see, which kind of makes sense, that the P70 data is really skewed far to the left, really low. P70 pushes a lot farther to the right, and P35 is does have some similarities to P70, especially where it's like its peak is, but it probably extends a little more out to the right than that. So this is kind of one way you can look at different, just the distribution of our different features. Did anybody try a different variable than mean diffusion coefficient and see something cool? If not, we're going to spend a couple minutes playing around with this. So please take a little bit of time to try to make and take base it. You can base it off of this one, but try a new variable, try a different number of bins, do stacked equals false, anything like that. So just try to change some stuff up. Could also try putting his type in there. So try doing something that's different than this, and then just put in chat if you want to what you changed, or feel free to speak up and let us know what looked different. I am gonna try to change the his type. Oh, that did. Oh, I don't like that better. So I put the bins up really high. I guess that looks better. Cool. Also, have people been able to get this figure to render, or are we running in any issues before that? Yes, totally. ECM goes. This one? Sweet. Oh, okay. Cool. Change asymmetry. All right, let me see. Oh, Laura, did you get the? Can I move away from this? Did you get it? Type error in this line. Is it mad at you for like trying to concatenate different types? Can only concatenate tuple, not list. Um, Yeah. Brackets are always annoying. Cool. So you got it to work? Yep. Awesome. Okay, let's check out mean asymmetry. I know copy and pasting is usually bad, but it's okay. Oop, that's why it's bad. Ooh, yeah, that does look different. Cool. Interesting that, yeah, I guess just like they seem like really similar distributions. That's cool. Okay, awesome. So now we're going to jump into a new type of visualization. So this is called oh gosh. ECDF is estimate. Oh god, I forgot the E is something cumulative distribution function. So you can really just think of it as a histogram, but I guess rotated, not like rotated on its side. And it's just something I get you'll kind of see, or I'll kind of once we visualize it, I'll show you why I like it sometimes better than a histogram. Um, so we're going to make a new function for it. So it's going to be called def ECDF f. And we're just going to have it take in one argument called data. And we are going to say that x is equal to numpy dot sort data. And then y is going to be equal to numpy dot a range 1 length of data +1. We're adding the +1 because a range is inclusive to exclusive. So if we didn't do this, it would miss one data point, which isn't the end of the world, but it's always better to keep as much data as possible. We'll divide this. Wait, when? Yes. Okay, we're going to divide out here. We'll divide also by length of the data. And then we're just going to return x and y. That should compile. Okay. So now we're going to make a new figure. And this is one is going to be um, a little more involved. So I'll try to go slowly here. plt.figure. So we're just going to initialize a figure. We'll say fig size equals 4 and 8. I just like kind of those dimensions. We are then going to get our x and y values for each of the different subset of data frames. So for the P14, P35, and P70. So say P14x and P14y equal ECDF. So the function we just wrote. And then we're going to pass it. Actually, I'm going to make one small change. So for my current code, that will be slightly better. We're going to say, what should I say? Feature equals, for now, we'll do mean def1. This is just going to make it easier to try out different features. So yeah, feel free to make that whichever one you want. But then we're going to pass our ECDF function, a numpy.array of P14 df of the feature we want to plot. So in this case, we're just going to put in feature. So now if we change it up here, it will also change it down here, which make it easier to change it for all three data frames at once. All right, so a little bit of repetition here. So P35X, P35Y equals ECDF numpy dot array, what is it, P35 df of feature. I'm just gonna make sure it runs and I didn't break something. Cool. Shouldn't plot anything yet because we haven't actually done any plotting, but I just want to double check that. I didn't break anything yet. P70X, P70Y. So same thing, ECDF numpy dot array P35 or P70 df feature. This is definitely not the most efficient way to doing it. Probably want a loop, but it works for now. Cool. So now we're going to actually make our plot. So we're going to do is we're just going to make three different scatter plots. So we're going to do plt dot scatter. So for the first one, we're going to do P14X and P14Y. We're going to label it, or label equals P14. And then we're going to just change the size, make the size of our scattered points. I like 3. Feel free to play around with that. Okay, so there's our, oh, that's kind of big. Let me make that. That's better. Cool. So this is the P14 data. So the idea here is that, and we'll get this when I add labels, but that this is 100% of the data, and this is 0% of the data, and this is the value. And so what this is saying is, so like here at 0.6, so 60%, this amount of data falls, or 60% of the data is under 25, and 40% of it is above 25. And here, like 90% of the data is under 50%. So it just kind of gives you it's very similar to histogram in that sense, but it's just giving like a very specific percentage of how much data falls under a certain amount of the data. And so the nice thing about what I like about this is it's really easy to compare distributions. I find it a little easier to understand than histograms sometimes when they get messy. So let's see, we can do a plt.scatter, and we're going to add in our P35 data. So P35X, P35Y, label is going to be equal to P35, and we'll make it S equals 3 again, and hope it runs. Cool, so we can see that their distributions are different for mean diffusion coefficient. And so one of the common ways of interpreting this is that 50% mark. So like here, and so we can see about the distribution is that 50% of the data for P35 falls under like, I don't know, like 10, whereas the 50% mark for P14 is 50. So that's kind of getting an initial sense of how these distributions are changing. Finally, we'll do plt.scatter for P70, P70X, P70Y, label equals P70, and S equals 3. And then we're just going to do some quality of life stuff for the plot. So we're going to say plt dot y label. Oops, y label. So this is just a function we can call on the figure object. So we're just going to write percentage sign. We'll say on our font size to be equal to 15. Yeah, that's good. And then we'll do our yx label, plt.x label. And we're just going to call this feature. so that it automatically chooses whatever feature we're analyzing. Feature, and you can do font size equals 15. Finally, we do plt.legend. So this again will just put the labels up on there, so it's easier to read it, hopefully. Oh, text is no object font size. Oh, that will be the issue. Cool. So now we can see that kind of similar to the histogram, which is good because they really are measuring very similar things. That these two, that the P35 and P70 have pretty similar distributions for the mean diffusion coefficient. And then P14 is a little bit more skewed to the right. But this max value of P35 is generally higher than that of P70. So this kind of confirms what we saw from histogram. I just think it's a little nicer to look at, but I think both are generally good visualizations. All right, so similar to before, can you spend like a couple minutes playing around with maybe just 1 minute since there's not too much else to play around with. Just try a new variable instead of mean diffusion coefficient. So I already forgot which ones we have. All right, I'll do mean boundedness. Mean boundedness. Oh, interesting. So in this case, distributions are much more similar for P14 and P35. 7. You can also try playing around with the size of the dots, although I think the bigger you go, the more confusing it will get. Not really. All right, did anybody else plug in a different variable and see a different trend compared to the mean diffusion coefficient? Did people plug it in, or people having trouble? Cool. All right, so there's another plot that I really like called the violin plot. And again, this is pretty similar. Like it's getting at the same thing as histograms and ECDFs are. That's really looking at a specific variable, and we're going to look at its distribution. But the nice thing about violin plots is they're like even more well separated in terms of how the data is being plotted between each class. And it just gives it's also just kind of a cool looking plot, in my opinion. So, and this is also really easy, which is nice. It's just like one line of code because we're going to use Seaborn for it. So let's do SNS dot violin plot. So really easy. We're gonna set a y value, and this y value is just going to be equal to whatever variable we want to be probing. So again, I'm going to use mean def1 for now, but feel free to try any other one. We're going to say x is equal to age. So this is telling us how we should categorize the data so that so we'll go look, you'll see that there are 3 unique, like the 3 unique ages in the age column, and it'll make different plots for each of those. So yeah, Seaborn is just really nice in terms of its ability to do easy stuff. And then data equals ECM. So this is just passing it the data frame. So this is like kind of all the stuff we had to do, like up here just to make this work. This is going to do the same thing, just literally in one line of code. So Seaborn is really, really sweet. And we're going to see that there's still kind of the similar trends of P14 going really high, P35 kind of being in the middle, and P70 being kind of low and spread out. So the way you can interpret these graphs is how high they go on the x-axis, or sorry, the y-axis is just like the actual value. So as you can see, like again, here's like the 150 marker. This is like what, 5 or 10. This is around 25. So that's just the value of the variable. And then the width is similar to just the height of a histogram. So if it's wider at a certain point, that means more data points are within that, near that value. So you can see like there's a ton of data points really low here, and this doesn't really have any one place where there's a ton of them, but most of them are around 25. And so this generally agrees with the trends we saw in the histograms. But because there's like this some kind of outlier data and then diffusion coefficient, this does look kind of messy. So let me try another one. I like boundedness. So yeah, this you can see instead of going up to 156, it only goes up to 0.4, which makes sense. So you can get a sense of that, this this big bulky part is lower compared to being very similar for P14 through P35, which is again what we saw in our previous plots too. Let's try, okay, what one haven't I tried yet? Do alpha. Oh boy, some outliers. But interesting to hear, it doesn't seem like the alpha is very different between the different classes. So when we eventually put this in machine learning, we could kind of think that like maybe this is a statistical feature that isn't really driving big differences because the plots, like the means are really, really similar. So the model wouldn't learn as much. So those are just some of the plots I like for feature distributions. We're going to talk about one more. This is going to be our biggest function. And this is kind of like tying in how we can, if we know specific things about the underlying data set, about like biologically, we can leverage that to making specific plots. So here, we're actually beginning using this alpha value. And alpha is it's like you don't need to know like the specific formula that it comes from, but it's an exponent of the diffusion coefficient formula. But one way it's used in literature is if it's less than 1, if a trajectory has an alpha value of less than 1, it's called subdiffusive, so it's moving slower than just random Brownian motion. If it's around 1, it's random Brownian motion, so it's just moving completely randomly at a normal pace. And if it's higher than 1, it's called super diffusive. And so it means it's moving faster than just random motion. And this can tell us a lot about the structural environment. If we have a lot of fast moving particles versus a lot of slow particles, this is really informative to what the actual differences in the brains are. And so even though just from this, it's kind of hard to see trends, we could potentially look at if there are differences in the distribution of those 3 categories and try to get some insights from that. So this is going to be another bulky function or bulky line of code, but I do think the plot at the end is pretty cool and useful. So before we go on, have people been able to get through making the violin plot? Sweet. Cool. And if you're running any issues too, this will all be recorded. And I'll put out the final notebook too. And okay, so we're gonna start a new figure. So figure equals plt dot figure. Let's do 4 by 6. big size. No, okay. All right, so we're gonna make a labels variable. And again, this is kind of similar to what we've done before, just so we can know what corresponds to what. So label is going to be equal to ECM age dot unique. So this is just going to say, okay, look in the age column of the data frame and just give us a list of the unique values, which will just be P35, P70, P14. Oops, don't want to undo that. We're then going to do labels dot sort just to get them in numerical or alphanumerical, I guess, order. Okay, so now we're going to calculate the percent of each of those three different motion types for each class. So what we're going to do is say directed. Actually, we'll change this. This will be super. So this is super diffusive. It's going to be equal to numpy dot zeros len labels. So we're just kind of initializing an empty array that we're going to plug our values into. So we're going to do a loop. Say, oops, Brownian equals numpy dot zeros len labels. Okay. And then subdiff for subdiffusive, because you just do sub, but numpy dot zeros len labels. Yes. I'm just gonna run it. You don't need to run it, but simply shaking it and break anything yet. Okay, so now we'll write our loop. So we're gonna say for I unique underscore class. So we're basically doing here is we want to loop through both the name of the specific age that we're using as well as the index that it's at, so we can basically put it into the same index of the array. And we're going to use this function called enumerate. Basically all this does is, instead of like a classic length, like taking the length of something and cycling through an array of numbers, you both get out the index and you get the actual name or actual value that's at the index. So we'll do labels. So this will give us this, looking at this sorted list here. We're gonna print. You don't have to do this. I just like to do this as a sanity check. Unique class, just to make sure we actually cycle through with all the unique classes. And then we are going to make a new data frame, which is df equals ECM, and we'll filter it by the age column. And this is going to be equal to our unique class. So here we're just getting a data frame for whatever the unique class is. So will just be P14, then P35, then P70. So we can then make calculations on those individual subsets. Okay. So we're gonna make a super df for our super diffusive. Super df equals df alpha greater than 1.1. So go into this data frame, and because our super diffusive particles are going to be ones that have an alpha greater than 1.1, we're just going to get a data frame that's just trajectories with an alpha greater than 1.1. In theory, we would do anything above 1 or exactly 1, but just because there's going to be very few particles that have exactly an alpha value of 1, then we basically have nothing in Brownian. So we're going to have that as between 1.1 and 0.9 is going to be Brownian. Anything outside or under that is the other two classes. So that's why it's a 1.1 instead of just greater than 1. Then we'll say super. So this is going back to our array here. Super I. So the ith index, so first and second and third, is going to be equal to the length of the directed data frame, or so what is that? The length of why am I confused? I might confuse myself. Did I miss something? Oh, sorry, I did. Length of super df divided by the length of the actual data frame. So this is just giving us what percentage do super diffusive particles make up of this entire data frame. And then we're just going to copy this code basically for the other two. So let's say our Brownian df equals df alpha. And we're going to have this one as less than or equal to 1.1. Oops, sorry, we need a parentheses here because we are then also going to we should need two parentheses. No. And I'm doing something wrong. df and df alpha greater than equal to 0.9. And then we'll close that off with brackets. Did I do that wrong? I'm gonna see if this breaks or not. Okay, I did break it. df okay, we do not need that bracket because that bracket goes there. Okay, that should work. What? Oh, I didn't. Oh, I did. I forgot that I took alpha out. So we'll just do mean alpha. Mean. Cool. Okay, I haven't plotted anything yet, but at least it does not break. So that's a plus. Okay, then we'll say Brownian I equals len of Brownian df divided by the length of normal df. And again, we'll repeat this one more time for subdiffusive. So we'll say sub diff df is df mean alpha. And this will just be less than 0.9. And we'll say that subdiff I is equal to the length of subdiff df divided by the length of the normal df. Going to double check again that this didn't break anything. Cool. Okay, so that's going to kind of set up our fill up our arrays that are telling us the percentage for each of the different age variables. Okay, so now we're going to actually make our plot. So we're going to say bar w equals 0.5. This is just the width of the plots we're about to make. We're going to make a bar plot, stack the bar plots essentially. So plt.bar labels. This will be, we'll do subdiff our label will be subdiffuse, oops, label equals subdiffusive. Our width be equal to bar W. So we just have it out here and then in here, so that's easy to change if you want skinnier or thicker ones. I am going to make mine a very specific colors. You do not need to do so if you don't want to. But I'm going to say color equals B7A57A. There is a reason I'm choosing very specific colors, but we will get there. All right, so next we're going to do plt dot bar. Again, labels. And then again, we're going to do Brownian. And then because it's stacked, we're going to say that bottom, so what is underneath this this specific bar stack, or the specific bar, is going to be equal to subdiff. So we just want it to be stacked on top of the subdiffusion bar plot. So this one, bottom equals subdiff. In this case, we're going to say color equals, how many nines is that? 6 nines, I believe. Hopefully I got that right. Our label be equal to Brownian. And our width will be equal to bar width. Last one that we'll make, labels. Oops, not that. Labels. This will be our super. Our bottom in this case is going to be equal to subdiff plus Brownian. So we want the bottom to be both of these. So this should be stacked on both of them, on top of both of them. Our color is going to be equal to 4B to E83. Our label will be label equals super diffusive. Oops, super diffusive. And our width again will be equal to the bar width. Cool. So this is the main part of it, but we're going to do some quality of life stuff. So plt dot ylim, going to set this to be between 0 and 1. Going to add a legend, so plt dot legend. We're going to say that we want the location to be in the lower right. Feel free to play around with this. I think you can do like upper, lower, maybe even middle. This is just where I kind of like to have it put. And we'll say our font size equals 14. I'm going to do a title. So we're going to do plt.title. And feel free, if you don't want to add these things, don't worry about it. It won't really affect the plot too much. I just want mine to look nice. So this will be percentage of diffusion modes per age. Font size equals 15. Gonna do, okay, legend. Then we're gonna do plt.xtix. Font size equals 15. So this is just kind of like our labels that are gonna, or like just the sides and the bottom of the chart. plt.ytix font size equals 15. All right, now we hope it compiles and runs. It did not. Okay, what did I do wrong? Not a valid color scheme. What did I do wrong? Put a Y instead of a 7. What? Is it another? But okay, that lower right's not valid. What? Oh. Oof. There's a lot of errors. Okay, there we go. Okay. So now we have our stacked bar plot. And so the reason I chose those specific colors is because they're Husky UW colors. I kind of like making that as a nice color scheme. So our subdiffusive trajectories are this gold, our Brownian are these the gray, and our purple are this super diffusive. And so here then again, even though if we look at this plot, it's kind of hard to pick out differences between any of the classes. Now we can see that if we kind of divide it down even further, that the distribution of different types of motion from P14 are really different from P35 and P70. And it's just something I like. You can see that a little bit here, maybe, but I think it's really more pronounced here. And specifically, we can see that even though Brownian motion stays about the same, the P14 class has a lot more trajectories that are moving fast compared to the other two. So again, this just gives us a lot more insight into specific aspects of the trajectory motion, which hopefully will can start telling us information about the brain. Yes, totally. So yeah, once this is kind of where we're gonna end for today. So the goal here is really to give you before we jump into machine learning, which I love talking about. I think again, really, it's really important to understand our data. And so hopefully now when we jump into more machine learning stuff, you can bring some of this knowledge about what variables are different or aren't different, what the distributions of them are into when we start building these models to really understand how the machine learning actually connects to biology, to brain structure, and to the underlying data. So yeah, I think that's pretty much it. We're at about 90 minutes, which is perfect. Yeah, again, this is all recorded. Final notebook will get up soon. I'm happy to talk about this, and I think I have office hours coming up soon. So any questions related to this, feel free to ask. Happy to take any questions now too for the next few minutes, but other than that, feel free to hop off and enjoy the rest of your evenings. Thanks so much for joining me.
Thank you so much. Bye.
See you later.
Thank you.